Right, so Kepler's second law, much like the first, can be stated in words, which is a line joining the sun and an orbiting body an orbiting, an orbiting body is fine, sweeps out equal areas during equal intervals of time. So we can draw a picture just to help visualize this. So imagine that here's our very elliptical orbit. Maybe the sun is here at one of the foci. Then we can imagine if we have an orbiting body following this ellipse, say at one point it's here, at another point it's here, at a third point it's here, and at a fourth point it's here. We can draw a line connecting, connecting the sun and the orbiting body. Let me just put the sun there. And so the point of Kepler's second law is that it lets us relate, it's just very hard to draw a narrow triangle, helps us relate the area of these two cone-like triangles. So let's say that it takes time delta t1 to go from, say, point A to point B. And let's say it takes delta t2 to go from point C to point D. And these areas, and when I say area, I mean like the geometric area that it traces out. These areas, call them A1 and A2. So Kepler's second law says if A1 is equal to A2, then delta T1 is equal to delta T2. And vice versa. If delta T1 equals delta T2, then A1 equals A2. So this might be a little bit surprising because it's not quite clear intuitively why this has to be the case, right? But this was something that Kepler observed, like empirically. He used a telescope, he noticed this, and he noticed it for all of the planets, and so he wrote it down and made it a law, and it turns out that it's actually a good approximation of reality. Now, there's a strong implication of this statement, right? The implication is that the average speed when going, say, from C to D is greater than the average speed when going, say, from A to B. And the reason for that is because in this angle here, theta 2 is larger than this angle here, theta 1. And so, and further, this triangle is shorter. So it has to be wider in order for the area to be the same. And so if it's wider, it means that it's traveling a larger distance. It's traveling a larger distance over the same amount of time. Basically, yeah, if the areas are the same, but theta 2 is bigger than theta 1, that means that the distance C to D is bigger than the distance A to B. And so if they occur in equal time, but the distance of one is larger, then the average speed of the one that travels a farther distance must be greater. And hence we get this implication. Now, what that implies is that in general, objects move faster near perihelion. Remember how we defined perihelion? It was the closest distance that an object is in its orbit with the sun, or about the sun, than aphelion. So this just says objects, the tangential speed, i.e. the speed that it goes around the orbit, is larger when it's closer to the sun. And in fact, it'll be largest when it's closest to the sun. And this kind of makes sense, at least it should make sense intuitively. When the object is far away and it's coming in on its orbit, what it's really doing is it's falling towards the sun. And so just like when you drop something on Earth, when it's falling towards the Earth, it picks up speed. So even though it's eventually going to miss the sun because its orbit is, or because it's moving too fast effectively, it still does gain speed as it approaches the sun. Eventually it'll swing around the sun and start and be thrown away from the sun. imagine like throwing an object up on the surface of the Earth. As it gets further away from the Earth, it'll lose speed. So it'll reach its maximum speed at perihelion, and then it'll fall away from the sun, not fall, rise away from the sun as it loses speed up until it gets to aphelion, which is its slowest point. Think of that as like the top of the arc when you throw a projectile. And that, I mean, you can do a lot with this. We can actually derive this statement from Newton's law of motion and from Newton's universal law of gravitation, but we'll save that for later today. But I just want to move on to Kepler's third law. This is just a useful statement, and it tells us about the orbital speeds at various places in an orbit. So let's move on to Kepler's third law. So Kepler's third law is a big one, and again, can be written out in words. This is like, these are the traditional words that are taught to students. That's why I'm giving them to you. So the square of the orbital period of an orbiting body is directly proportional to the cube of its semi-major axis. Now remember what a semi-major axis is. The semi-major axis of an ellipse is half of the long distance, not semi-distance, sorry, semi-major. So it's, if you drew a line, I'm going to erase it, but if you drew the line from one end to the other, starting at or going the long way, that is the major axis, and so the semi-major axis is half of that distance. It's like the long radius of an ellipse. The semi-minor axis would be like the short radius of an ellipse. And so we can represent this law mathematically by using the variables that we have learned to use for things like period, orbital period being t for time. Remember that was the letter that we used for the period of precession. So capital T is often used for the period of some sort of revolution. And A for the semi-major axis. So this would say the square of the orbital period, t squared, is directly proportional, proportionality symbol, to the cube of its semi-major axis, so A cubed. And this is a useful expression. We can actually rearrange this proportionality and get that 1 is proportional to, now this is a weird thing to write, but it's proportional to A cubed over t squared. Now, what does it mean for for something to be proportional to 1? What it means is that that thing is just constant. And so we have this relationship for Kepler's third law. A cubed over t squared is some constant, some yet to be determined constant, but it is constant, and that's the important part. And the reason why this law in particular is particularly strong is because it says something along the lines of, if you know the properties of one orbiting body around, say, the sun, and you know some of the properties of another orbiting body, you can determine all of the properties of that second orbiting body. Like, for example, let's say that we knew the distance that the Earth is from the sun, i.e. its semi-major axis, and we knew the duration of, or the period, the orbital period of a single revolution, which would be 1 year, right? That's how a year is defined. And let's say we also knew how far away Mars was from the sun. Using this relationship, we could figure out how long it takes for Mars to go around the sun. And the reason we could do that is because the constant only depends on the thing that you're orbiting around. And since they're both orbiting around the sun, they both share the same constant. So you could use Earth's relationship, what you know about Earth, A cubed divided by t squared, and just figure out what that constant is. It would be the Earth's distance from the sun cubed divided by 1 year squared. And then you could use that constant, plug in the distance that Mars is from the sun, A cubed, and then solve for t to find the orbital period. So you only really need to know one of these parameters as long as you know both of them for one orbiting object. So this is a really useful thing to do. And this is probably one of the reasons why Kepler is famous, because it was used to calculate these sorts of things. Now, keep in mind, this Kepler's third law, this relationship, can actually be derived with Newton's universal law of gravitation. Like you could figure this out with Newton's universal law of gravitation, but the part that makes it remarkable is the fact that Kepler didn't know that. This was before Newton's time, and so he kind of just noticed these patterns amongst the planets orbiting. And this is with like really bad telescopes of the mid 1600s that are made out of ground glass and have apertures like this big. So it says something about how clever he was. So let's use this in an example. So maybe we ask the question, how high must a satellite orbit? So satellites orbit around the Earth, right? At least some of them do. Not all of them do, but some of them do. How high must a satellite orbit above the Earth to ensure that it is always above the same position on Earth? Now, first we have to kind of decipher this word problem. A priori, this might seem like a very strange thing to ask, right? How could it be that something could orbit the Earth and yet not go over different parts of land? It's traveling so fast. But keep in mind that the speed that an object orbits something with is related to how high it is, right? You can orbit more slowly if you're higher up, and that's because the gravitational pull is effectively lower. Now, another point to make is, what does this, if a satellite indeed just stays above a single point on Earth, i.e. you launch it up and it's just always directly above you at night, during the day, whatever, what does that imply about that satellite's orbit? Well, it implies that in the time it takes for you to have a day-night cycle, i.e. in one day, it has to orbit around the Earth exactly once, so that as you rotate, it moves with you. So what that means, on a most basic level, is that it has to have an orbital period of exactly 1 day. That way, it will always stay above you, assuming that you are on the equator and it is on the equator. Or rather, it has to be, yeah, that's the true statement. It's orbiting above the equator. So now we can use Kepler's third law, or at least we can try to use Kepler's third law to figure out how far away it must orbit the Earth from. So I'm going to call it K3, and we're going to assume a circular orbit. All of Kepler's laws, by the way, apply to circular orbits just as well, because a circle is just a special case of an ellipse with no eccentricity. This is what that little e is, eccentricity. So Kepler's third law tells us that a constant, some constant, which we don't yet know, is equal to the radius of the orbit, which is what we're trying to find, squared, or cubed, divided by 1 day squared, because that has to be the orbital period. Now the trouble is we don't know what this constant is yet. But what we can do is we can use Kepler's third law to determine what that constant is by knowing properties of another thing that's orbiting the Earth. In particular, the moon orbits the Earth, so we can use what we know about the moon to figure out that constant. So in particular, first we need to know how long it takes for the moon to make one orbit around the Earth. It turns out that that's something that you can just figure out. It's the time between full moons, or roughly the time between full moons. So the moon has an orbital period of about 27.32 days. Just is what it is. We also need to know how far away it is from the Earth. That would be its semi-major axis, right? This is the distance between the source of the gravity and the thing doing the orbiting, at least for a circular orbit. And this is something that we must know, if only because we sent people there. But even if you didn't know this, you could work this out by, say, shining a laser on the moon and figuring out and counting how long it takes to come back. divide by the speed of light. That would be another way of doing it. Turns out that the semi-major axis is about 384.4 megameters, or 1,000 kilometers, right? So we can use both those data to figure out what the constant is. So that would imply that 384.4 megameters cubed, which is a huge number, by the way, divided by 27.32 days squared, this should be equal to the constant. And that constant is then going to be equal to the distance that our satellite should be from the center of the Earth cubed divided by 1 square day. It's a weird thing to say. So pulling this in, then we get that this is equal to r cubed, the orbit, divided by 1 day squared. Right, so now we just have some math to do. So we can simplify this expression, and we get that this left-hand side is 76,458, approximately anyway, megameters cubed per day squared. And so that is equal to r cubed orbit divided by a squared day. And now you can just solve. So that implies that the distance that our satellite must orbit from the center of the Earth is the cube root of 76,458 megameters, which is about 42.4 megameters, or about 42,400 kilometers. Now, remember, this is the distance from the center of the Earth, because when we're talking about orbits, these are the orbiting things are spherical masses. We treat them as if all of their mass were located at the center of the bodies. So this type of orbit that we've just described is actually called a geostationary orbit. Geo meaning Earth and stationary meaning it doesn't move. And that's just because if you launch one of these satellites into a geostationary orbit, if you were to look at it with a telescope, it looks like it just doesn't move because you're moving with it. And so this is a well-known thing. A lot of telecom companies have satellites in geostationary orbits. And so this is a thing that they need to know with precision. Our orbit is the distance. It is the distance from the center of the Earth to the satellite, it's like, let me draw a picture just so that I can be a little bit more clear. Earth is here. Here's our satellite. This distance is our orbit. It's just the orbital radius, that's all. Right, so this number has to be very well known in order to make these satellites be geostationary. And so you can actually go and you can Google what the height of the geostationary orbit is from the center of the Earth, and you can compare. And it turns out that the actual height is 42,164 kilometers, which is pretty close. Right, so certainly Kepler was onto something. This is a pretty good approximation, and really, like, the failures here are not the failures here are not just because of Kepler's law is bad. It's just because we made some approximations that we probably shouldn't have. So now let's talk about, so those are Kepler's 3 laws, by the way. There's only 3 of them. They're all relatively straightforward. But now let's actually derive them from Newton's laws. And in particular, this will involve Newton's universal law of gravitation. So let's start from the beginning, Kepler's first law. So Kepler's first law was a statement about that all orbiting bodies orbit in an ellipse, with the gravitating body being at one of the foci of the ellipse, and the orbiting body travels in an ellipse about that focus. So it's kind of hard to, some of this is kind of challenging to do, how do I want to phrase this? Yeah, I'm just giving you a warning. Some of this is a little bit messy, or not messy, but it's a bit involved to do a mathematical derivation. So do your best to follow along. And again, the notes will be posted. You can go back and watch the lecture at slower speed if you need to. Right, so we want to answer the question, why are the orbits closed? I.e., why is it that they don't just like trace out one ellipse and then trace out a slightly different ellipse and then a slightly different ellipse and so on? Why does it, when I say closed, it means it repeats back on itself perfectly every time. It turns out that in fact they aren't closed, but that's a higher order effect that Kepler's law doesn't really account for. And it's because there are other bodies in the solar system like Jupiter tugging on things. But in an ideal scenario, if there's only two orbiting bodies, it should be a closed orbit, i.e. just a simple ellipse that repeats itself over and over. So the question is why? So we can rephrase this more mathematically. Why, when going through an angle of 2 pi, remember, we can describe the position of the orbiting body around the focus with an angle and a distance. Is the orbital distance the same? So in order for it to be a closed orbit, every time you make one full orbit, which is 2 pi, an amount of angle traversed of 2 pi, the distance that you end up with should be exactly the same distance that you were from the focus to begin with. And you're at the same angle, so you're at the same position. So it's just you go through 2 pi and you end up back at the same position. Why does that happen? So I'm going to give you a rough proof, which it's rough, but hopefully it'll get the point across, of why this has to be the case. And this is going to use Newton's second law and Newton's universal law of gravitation. I'm putting this in quotes because it's not precise. So Newton's second law, and all of the applications of Newton's second law and so on that we're going to use here are going to be relevant for the orbiting body, not for the source of the gravitational force, because we're going to assume that that source is fixed in place. So let's start with Newton's second law, F equals ma. So first of all, we know what the force is. I'm going to write that on the right-hand side. It's the gravitational force. But the ma would look like m2. M2 is the mass of the orbiting body. Keep in mind that the gravitational force is g m1 m2 divided by r squared. So the m1 is the source of the gravitational force in our imagination. M2 is the mass of the orbiting body. This will become a little bit more clear here. It's the mass times the acceleration. Now it's a vector. And we can write the acceleration as a derivative of the velocity. So let's do that. It's just the time derivative of velocity of the orbiting body. And this is supposed to be equal to the gravitational force. Now that can be written as g m1 m2 divided by r squared, r being the distance between the two objects, the distance between their centers anyway. This negative sign is part of our direction, and the remaining part of the direction is r hat. Remember, r hat points from the sun to the Earth, for example. And so sticking a negative sign in front tells us that the direction of the force is from the Earth to the sun. It points, if you're at Earth, it would point you towards the sun. It's attractive. So now we can use the chain rule. There's going to be a lot of calculus involved here, so try to follow along. So using the chain rule, where dv dt is actually equal to dv d theta dt, right? That's just allowed. We can write this derivative as a derivative of v with respect to its angular position times the derivative of the angular position with respect to time. And we get that m2 dv d theta dt is equal to negative g m1 m2 over r squared r hat. Now, we have to use another fact. We know that the gravitational force is a central force, i.e. this force is pointing towards the sun. So what does that tell us? Well, it tells us that in particular, if this is the only force acting on our orbiting body, which is an approximation because there are other planets, but if this was the only force, then that would mean that the net torque on the body, because it's a central force, is 0, where the torque is calculated about the sun. This is the net torque on the body with the pivot point located at the sun. So let me just write that out. Gravity is a central force. So in this case, the net torque on the body is 0. And what that implies is that the angular momentum is conserved, L. And so we call L a constant of motion. So L is just a number that describes the orbit. It doesn't change regardless of where on the orbit the object actually is. So let's use what we know about angular momentum for any sort of orbiting body to to determine the angular momentum in terms of other variables. So let's say that you have the sun here, and let's say you have the planet here. So the angular momentum of the planet could be written in two ways. One would be would just be mv times mv times r, mv perp times r, but that's a little bit more challenging. Instead, what we can do is we can just use the fact that the angular momentum of a system is equal to the the moment of inertia of that system times its angular velocity. It's equal to I omega. And so in particular, the angular momentum, or the moment of inertia of a point mass, which we can treat the planet as a point mass here, is just mr squared. It's just the distance that the point mass is from the axis of rotation squared times its mass. That is the angular momentum. Sorry, that is the moment of inertia. And the angular speed is just d theta dt. It's just the rate at which the angle changes, right? So we can actually use this to solve for d theta dt in terms of L, which is just some number. So substituting that in, we get that m2 times dv dt, we're substituting back into Newton's second law. Sorry, this is dv d theta, times L divided by m2 r squared. This is what d theta dt is. And that should be equal to negative g m1 m2 divided by r squared r hat. And these r's are the same thing, by the way. They're both the distance from the sun to the planet. And so we can do some cancellations. M2 cancels M2. This r squared over here cancels this r squared over here. And so we're left with, after doing some more algebra, that dv d theta is equal to negative g m1 m2 divided by L r hat. And this number here, this is just a constant. L is a constant, the masses are constant, g is a constant, and that's it. And this r hat is just the vector that has a unit length that points towards the planet at an angle theta. And so we actually know what the vector formula is for that. The vector formula for r hat is just cosine theta I hat plus sine theta j hat. And so that is dv d theta, I'm just substituting this in, is just minus g m1 m2 divided by L times cosine theta I hat plus sine theta j hat. And now we can do a trick. We can multiply both sides by d theta and integrate. You can always do the same thing to both sides. This, from the fundamental theorem of calculus, this just gives us v of theta plus a constant. As a vector. And then we can just do this integral. The only thing that depends on theta are these two terms, so we can just do those integrals. So we're left with v of theta is minus g m1 m2 over L. It's a constant, you can pull it out of the integral. Integrate a cosine and you get a sine. So sine of theta I hat minus cosine of theta j hat. Integrate a sine, you get a minus cosine. And then we have to add a constant, call it v naught, the vector v naught, because these are antiderivatives, so you need, this is like the plus c that you have to add. And so what does this tell us? So this tells us what the functional form is, but we're not quite done because we don't know what v naught is. And so it takes a little bit more work. First of all, note that v of theta equals v of theta plus 2 pi. Well, that has to be the case. R is not constant. There's no R here. That's the point. By writing it out in terms of angular momentum, we've eliminated R from the problem, and that was the reason why we did that. And this R hat, that's certainly not constant. That's a direction that's changing with the angle, but that's just a function of an angle that we can integrate. So first thing to note is that if you add 2 pi to any choice of theta, you'll get the same thing, because if you add 2 pi to this bit, to that theta, you'll just get sine of that thing again. And if you add 2 pi to this theta, you'll get cosine of that thing again, because both sine and cosine are the same if you add 2 pi to whatever angle they're acting on. And so from that, we learn that v squared of theta is v squared of theta plus 2 pi. So by the way, what this tells us so far is that the translational speed repeats itself every 2 pi. But that doesn't yet tell us that the distance repeats itself every 2 pi. You could, in principle, integrate this, but then you would have a constant that you don't know how to handle with, and that would be a constant times theta, and that would not repeat itself, right? A constant, like theta would go to theta plus 2 pi if you added 2 pi to theta, right? So that's not enough. But what we can do a little bit more. We can do something a little bit trickier. We know that the square of the speed is constant, or is the same if you add 2 pi to theta. And so that tells us that the kinetic energy as a function of angular position is the same as if you took the kinetic energy at that angular position and added 2 pi to it. This is all kind of trivial because the speed is the same. The speed and the direction are the same, so if you add 2 pi, then the speed and direction will still be the same, so the kinetic energy is the same. But here's an important point. Gravity is a conservative force. So what that means is if the change in kinetic energy over one full rotation, i.e. after adding 2 pi to your angle, is 0, that implies that the change in potential energy is also 0, assuming there are no external forces. And now I haven't told you the formula for the potential energy due to gravity. We'll cover that on Wednesday. But what I can tell you is that the force only depends on this vector r. So the potential energy should only depend on that distance r. The potential, the fancy potential energy for gravity only depends on r, the variable, which is the distance from the sun to the orbiting body. And so what that means is that if the change in the potential energy, the gravitational potential energy, is 0, that implies that the change in r is 0 as well, because there's no other dependence in that function. And so what we've then concluded is that r of theta is equal to r of theta plus 2 pi. i.e., after you go through one orbit, you come back, or after you make one full rotation, the distance that you're at is the same distance that you're at before you went through one full orbit. And so this is the proof, or at least a proof, that the orbits are closed, i.e. that you end up back where you started after one full rotation. It didn't have to be that way, but it's sort of a coincidence of well, I'll tell you. As a quick note, this only worked. R could be a vector, but I'm writing the magnitude of r, or just the distance. In general, r is a vector, but r, when I just write r, this is the magnitude of the vector r. That's all. It's the standard thing that I do. This only worked because the force of gravity was proportional, or was inversely proportional to the square of the distance. if we go look up here, the only reason we were able to cancel out that value of r is because it was r squared in the denominator of the gravitational force. If it were r cubed, this would not have worked at all. We would, and in fact, this is just a true statement. If you have a force that depends as 1 over the distance cubed, 1 over the distance to the 4th power, or 1 over the distance, you don't get closed orbits, i.e. the orbits will never repeat back on themselves, which is kind of convenient then that we have those, because otherwise planets wouldn't have formed and there wouldn't be life. And it turns out the reason we have why gravity goes as 1 over r squared is because we live in a 3-dimensional universe. So that's a reason why there are 3 dimensions instead of 4 or 2, because if there were 4 or 2, then there would be no planets, or there would be no stable orbits, and if there's no stable orbits, there's no life, and so on. Now, so just as a hint for problem 6 on the homework, you're going to have to use some of this material. This is about finding the ratio of the speeds or of the velocities at perihelion and aphelion. What you want to use, the fact that you want to use, is you want to use the fact that L is conserved. And that the angular momentum can also be written as mv/r perp. Those will both be very useful. The result that you end up with for number 6 should be in terms of the eccentricity of the orbit, E, and the semi-major, and perhaps the semi-major axis. So those are the only variables that you should have, or the only parameters that you should have in your final form. Like you can have a G, like a capital G floating around, or you can have masses, but the only parameters that should be there for ellipses should be E and A. Now I'm going to skip a whole bunch of work, some of which involves solving problem 6, and I'm going to show you a useful formula that you get from this sort of analysis, just from learning about the speeds that we had and so on. So this result will not be useful to you for number 6, so don't try to use it. Maybe it will be useful, but you're not allowed to use this fact anyway, just because you have to prove it. L squared is equal to A times 1 minus E squared times G times M1 times M2 squared. True fact. This number, this is a constant. And that is the constant that tells us what the square of the angular momentum is for any given orbit. And so I'm going to put in big capital letters here, do not use for number 6. If you do, you will lose points, because I skipped the work that I'm asking you guys to show. That involves getting here, and it also involves solving problem number 6. However, we can take this fact and we can substitute into the original formula for r of theta. This is the one I gave you on last week on Wednesday. We get the formula r of theta equals L squared over G. I'm going to use capital M for the source. What tells you? I mean L is angular momentum. Gm m squared times 1 over 1 minus E cosine of theta. This is a useful fact, because it means that you don't have to write it in terms of, or rather, it's just a simpler version that depends only on the angular momentum rather than the semi-major axis, right? All right, so now we can move on to Kepler's second law. Hopefully we will get through here. So Kepler's second law, and we're going to do another derivation. So this is the one about sweeping out equal areas in equal times. And so we're going to examine the infinitesimal version, i.e. if you take an infinitesimal amount of time the orbit will trace out the same equal infinitesimal amount of area, regardless of where you are in the orbit. So the picture here is you have your ellipse, you have your body, and then you're sweeping out an infinitesimal area. It's hard to draw infinitesimals, but bear with me. D theta here, this distance might be r. Here's the arc that's swept out. This distance here is dr. It's a little bit more of the, it's the amount of radius that you add after you travel d theta. So this distance here is r plus dr. And so this is r. Now this distance, just from our standard circle mechanics, and we can approximate this as a circle, because we're just basically tracing out a circle here. I'm not going to draw that, but that's the idea. That's what that arc is for. That arc is for a circle. That distance is r dr. That's the height of our triangle. So we can actually use this sort of drawing to figure out the area of the triangle. So the area of a triangle is 1/2 base times height. And this is approximately a right angle, at least in the infinitesimal limit. It's a right angle. And so we can just multiply base times height, and then for both of these two tiny triangles, and then add them up. So dA, the infinitesimal amount of area that this whole arc traces out, this would be equal to 1/2. Let's do the big triangle first. It's times the base, or the base, which is r. That's this distance, it's the base of our triangle. 1/2 times r times the height, and the height is that little arc times r dr. And then we have to add the remaining bit, which would be 1/2. The base here is, sorry, that's not r dr, that's r d theta. R d theta. It's an arc length, right? The base of that other triangle is dr, this triangle, that's that base, times the height, which is also r d theta. And so we can simplify this. This infinitesimal triangle is 1/2 r squared d theta plus 1/2 r dr d theta. Now, let's divide by the amount of time it takes. Well, this is an infinitesimal area, so it'll take an infinitesimal amount of time. So we have dA dt, which is the amount, we're just dividing by the rate at which, or the amount of time it takes, would be 1/2 r squared d theta dt plus, and now we're kind of stuck, but we have to choose one. So this is r dr d theta dt. I just chose one of them. But the important point is that in the limit, where dr, d theta, and dt all go to 0, these fractions stay constant, right? A derivative is a limit where d theta and dt, or dA and dt go to 0, but the ratio of those two things doesn't go to 0. However, this one, this dr, is alone. So in that case, this in that limit, this whole thing, that term vanishes. So what we're left with is that dA dt, the time derivative of the area. So the area will increase as you increase this theta. So imagine you're here. After a little bit of time, it's this big. After an even longer time, it's this big, and so on, right? That area increases as time passes. So the time rate of change of that area is just 1/2 r squared d theta dt. And so d theta dt, that is just the angular velocity, right? So this is 1/2 r squared omega. Now again, angular momentum is constant here because gravity is the only force, and gravity exerts no torque from the center of, from the gravitating source. So we can write this, after a little bit of simplification, or after a little bit of manipulation, we can write this as m r squared omega divided by 2m, multiply and divide by m. And this term up here, that mr squared is I, that omega is omega, it's the angular velocity, so this is just L over 2m, which is a constant. So what this tells us is that the amount that the area grows by every millionth of a second is the same, regardless of where you are on your orbit. So already that should tell us that the second law is probably right, because if you're on one side of the orbit, if you wait a millisecond, your area will increase by some amount. And if you're on the other side of your orbit, if you wait the same amount of time, a millisecond, the area will also increase by that same amount. But just to be double sure, we can integrate this formula, dA dt is equal to that, in order to find the area of some fixed duration slice that an orbit sweeps. So we have dA dt is equal to L over 2m, L being the angular momentum, which tells us that dA is equal to L over 2m dt, or after integrating, we get that A is equal to L over 2m times delta t. So this is the area that an orbit sweeps out in time delta t is equal to the duration times the angular momentum, L, divided by twice the mass. And that's it. That is the area, and you can check that the units actually make sense. So this is just Kepler's second law, K2. Kepler's second law says that it doesn't matter where you are in the orbit, the area is always the same, and the important point about this equation is this area doesn't care about where you are in the orbit. It's just, it only depends on your angular momentum, which is constant throughout the orbit, and it only depends on the duration over which the area is being swept out, which you choose to be the same. All right. I have a little bit more to go, so we might run a few minutes over, but I want to get through K3, Kepler's third law. And so first we're going to check it. So Kepler's third law was the statement that the cube of the semi-major axis divided by the square of the orbital period is a constant for any body that's orbiting some particular body like the sun. So let's check it for circles first. It's a little bit harder to do for ellipses because the semi-major axis, or the distance that the object is from the sun or from the gravitational source, isn't constant, but for circles it's easy. So in a circular orbit, we know that the velocity is constant, right? It travels around the sun at a fixed rate. So the velocity is equal to the average velocity, and the average velocity you can just find by taking the distance covered divided by the time it takes. The distance covered would be 2 pi times capital R, that's the orbital radius. You divide it by the orbital period, t. Easy peasy. Now, Newton's second law gives us that the magnitude of the force should be equal to the mass times the magnitude of the acceleration. The magnitude of the force is, let me use lowercase r here, just for consistency. The magnitude of the force is gm1 m2 divided by r squared, and the magnitude of the mass, m2, times the acceleration, a, well, it's a central force, right? It's always, the force is always pointing towards the center, and because it's circular motion, we can characterize that as a centripetal acceleration, right? So this is m2 times v squared over r. And so what we find, we can do some algebra to this, relating r to, substituting in that v is 2 pi r over t. Something's wrong with my calculation. That's annoying. Oh, no, never mind. Ignore me. I'm just being dumb. We can solve for v squared in this formula. So v squared in this formula is just gm1 over r. So now we can use these two equations to eliminate speed, right? So from the first equation, we have 2 pi r divided by t squared is equal to, that's v squared, I just took this and squared it, is equal to gm1 over r. And so we can actually just relate these, or we can use these relationships, simplify things and rearrange, and we find that r cubed divided by t squared is equal to gm1 divided by 4 pi squared. But importantly, this is a constant because M1 is the source of the gravitational field, and so it doesn't depend even on the mass of the object that's doing the orbiting. So Kepler's third law works for circular orbits. For ellipses, it's a little bit more challenging. I'll take like 5 minutes to go over it, and then we'll be done. But it amounts to much of the same. It just requires a little bit of elliptical geometry. So first, we need to actually know the area of an ellipse. The area of an ellipse, there's a nice, neat formula for it. It's just pi times AB, where A is the semi-major axis and B is the semi-minor axis. It's the shorter radius. So Kepler's second law would tell us that the area swept out is equal to L divided by 2m times delta t. This is just that if you sweep out a full orbit, this tells us the area of that orbit as it relates to the duration that it takes. So for the whole ellipse, the area of the ellipse is L over 2m times the period, t. So now we can just set these two things equal to each other, this and this. We get that pi AB equals L over 2m times t. Now there's some geometry here that we can use. Turns out that b squared is equal to a squared times 1 minus the eccentricity squared. You can work that out using just the standard elliptical geometry. We can square both sides and then substitute this equation in, and we get that pi squared a squared times a squared 1 minus e squared is equal to L squared over 4m squared t squared. I just squared both sides and substituted in. Do a whole bunch of canceling and simplification, and you end up with a cubed divided by t squared is equal to g, was I using little m or big M? I'll use m1, g m1 over 4 pi squared. Which, if you look above, it's the same formula that we had there, so it's just a little bit harder to derive for an ellipse. For a circle, A is the same thing as R. The radii are the same. So the whole point is that indeed, the cube of the semi-major axis divided by the square of the orbital period is a constant, and it only depends on the mass of the thing that's causing the gravity. You multiply it by a gravitational constant, divide by 4 pi squared, and that just is the number you get. So in fact, we could have used this to find the geostationary orbit if we knew the mass of the Earth. That's a little bit harder to do. Now, just as a quick thing to say, and then we'll be done, we had to use the fact that the orbit was shaped like an ellipse here, right? Because we had to use this fact that the orbit was elliptical. And in fact, the orbit is only elliptical if it's closed. So we needed to use the fact that Kepler's first law was true in order to derive Kepler's third law. And Kepler's first law required that gravity goes as 1 over r squared. So both Kepler's first and third law require that gravity is proportional, is an inverse square law. The second law wasn't, you didn't need the inverse square law property for gravity for Kepler's second law. You only needed that it's a central force. So they're kind of on different footings, the second law and the first and third, but just keep that in the back of your head. All right, so that's all I had planned for today. Sorry, I ran a little bit over.